Hi everybody, this is the second video going along with section 1.6, which will focus on tables of linear, quadratic, and exponential functions. And one of the first things that we need to put down is that there is no way to decide if a table is truly quadratic. So we're going to start out with that. There's no way to tell if a table is truly quadratic. You can estimate if it is because you'll see symmetry in the outputs, because we know that a quadratic has to look like this as a picture or look like this. So there has to be some sort of symmetry in the outputs, but there is no way to completely verify the symmetry if you don't specifically see it obvious. Okay, it would have to be really obvious that it's the same on both sides of a number, the same difference. So that means that we can kind of eliminate quadratics in this whole lesson, okay? So we're really only going to decide whether the table is linear or if it's exponential. So let's focus on just some examples so that we can see. We have our x and our y, and let's say that the pattern looks like this: -2, -1, 0, 1, 2. And we have -6, -4.5, -3, -1.5, 0. And we're being asked, is this linear or exponential? So let's do a quick recap of what we learned in the first video on section 1.6 about their graphs. To be linear, there has to be a constant change, which we had called the slope or the rate of change, okay? So to be linear, there must be a constant rate of change. And we learned that rate of change is the same thing as slope. I'll just put that in parentheses here. And we learned that slope is the change in y over the change in x. Okay, so we talked about that because we talked about it as rise over run. So it's the change in the y direction over the change in the x direction. So let's put this in different language now. Okay, yes, we're looking for that constant change, but what's really happening? We're saying for every constant difference in x, there is a constant difference in y. Okay? That's what we're looking for. So I'm going to give you a shortcut for how to do that in a table. First, look at how your x is changing. In this example, your x is always changing by ones. Well, that makes it a little bit easier because my x is a constant change. I just need to make sure my y is also a constant change. So look at the same thing. See if there's a constant change on the y side. To get from -6 to -4.5, I added 1.5. To get from 4.5 to -4.5 to -3, again, I increased by 1.5. And then I did it again, and then I did it again. Okay, so you can just do these quick little differences on the side and then see if you have a pattern. You're looking for that pattern. So if I look at the change in y over the change in x, because remember, rise comes first when you're talking about climbing a staircase, okay? So for slope, we're talking about y direction first. The change in y is 1.5. The change in x is 1. So that tells me that I do have a constant change of 1.5 or a slope of 1.5. Not only that, but I could also verify this graphically by plotting these points, okay? Some people are just spoken to more in pictures. So if you prefer actually counting rise and run, there is nothing stopping you from plotting these points and then counting your rise and your run. Just know that if you always have to go to a graph or some sort of diagram, it is going to take longer, and that's going to be an issue if you're doing this on a quiz or a test. So you do want to know some of these shortcuts, okay? You don't want to have to always go for the graph. Okay, so is this linear or exponential? Because I found a constant change, this is linear. So this is linear because for every one change in x, there is a 1.5 increase in y. Okay, so I can actually describe that. This is not all they're going to want to know. They're also going to want you to find all important features. Well, what are the important features if you're talking about a line? On a line, yes, the slope's very important, and we actually killed two birds with one stone with that, because just doing this test will find you your slope. So that part's done. I need to know the x-intercept and the y-intercept. So I want to find the x-intercept and the y-intercept. Now, graphically, we know these definitions. The x-intercept has to be where it crosses the x-axis, and the y-intercept must be where the graph crosses the y-axis. Okay? So, again, you could take these coordinates and you could plot them and see where they fall. But let's think about this logically. If I am on the x-axis, I'll just do a quick example here. Okay, a little sketch. It's not necessarily of this, just a little sketch. If I'm on the x-axis, okay, for the x-intercept, I did not move in the y direction. So that must mean that I'm looking for when y equals 0, because I didn't move vertically. Well, look up here and see when y equals 0. Y is 0 at the point 2, 0. So that's my x-intercept. Now, similarly, if I'm on the y-axis, I didn't move in the x direction at all. So my hint would be that x has to be 0, okay? Because I must be on the y-axis. Look up here and see when x is 0. X is 0 and y is -3. So that tells me that my y-intercept must be the point 0, -3. And I can pick that out directly from the table. Okay, so what do we know about this? We know if it's increasing or decreasing. It's increasing because the slope is positive. It's going up. We know what the slope is. We know the x-intercept and we know the y-intercept. So we have answered all the important features for this line. All right, moving on. Let's look at another table. Let's say your table looks like this. We have our x and our y, and your table is -1, 0, 1, 2. We'll just do that, and we'll do 2 as an output, 3, 4.5, and 6.75. And we want to know, is this linear or exponential? And then not only that, find all important features. So once we decide, then we want to go and answer the rest. So is this linear or exponential? Let's do a quick linear test first, because we just said to be linear, we have to look at that constant change. So x is changing by ones, okay? My y, you can already see with these decimals, is not changing constantly. From 2 to 3 is an increase of 1. From 3 to 4.5 is now an increase of 1.5. Definitely not the same. So we can cross out linear, okay? Because there is no constant addition. There is no constant difference in the input and output, okay? So no constant difference in input and output. All right, excellent. I'm able to rule that out. And I always recommend testing for linears first because it's kind of more of a visual test, okay? You can kind of spot the pattern. So now let's see if we can decide if it's exponential. Quick reminders of the last video. What does it mean to be exponential? Exponential functions have a constant factor, which I suggest you also know as a multiplier. Okay, we talked about that because that's literally what you're doing. You're multiplying the outputs. I'm looking to see if there's a constant multiplier for every constant multiplier on output for every one change in input. So first, let's see if we've met that requirement. We do have a one change in input. Excellent. So now we have to see if we have a constant multiplier as we move on. Well, if I want to test for multiplication, we talked about this in the last video, I need to divide going backwards. So I want to know what 3 divided by 2 is. Okay, we're dividing backwards. 3 divided by 2 is 1.5. I want to know what 4.5 divided by 3 is. Again, sequential outputs. I get 1.5. And you can do this with the aid of your calculator. Okay, so this is just, again, sequential outputs. That's where I'm getting this 3 and this 2 from. All right, we're going to learn function notation in a later video. Okay, but basically I'm evaluating always 1 more x divided by 1 less x. Okay. And then last but not least, because I do need to test all of them to make sure that the pattern is consistent, if I put that in my calculator, I get, again, 1.5. So yes, there is a constant multiplier. Okay? I can say this is exponential because every output is multiplied by 1.5 for every one change in input. So we already made that decision. And not only that, but by this very test, I also came up with my factor. So that's one of the important features. I can now say that the factor is 1.5. What does that tell me about this? That tells me, and not only that, but the pattern tells me that this is exponential growth because the factor is larger than 1, and I can see it in the pattern of the table. Okay. I also can pick out an intercept. The y-intercept is going to be 0, 3. Remember, always write it as an ordered pair. And the reason I know that it's 0, 3 is because the y-intercept occurs when x equals 0. You have not moved in the x direction, okay, if you're on the y-axis. So I can pick out that information. And then, last but not least, I need to figure out the rate of growth. I know it's growth. I know the factor. I need to figure out the rate of growth. Rate, remember, is the percent change. Factor is the percent you keep. If I convert this to a percentage, that means that I'm keeping 150% every time. Every time my next value is 150% of what it was previously. But I don't want to count the original 100. So I take away the original 100 and I'm left with 50%. So what am I doing there? I'm taking 1.5 and I'm multiplying by 100, and then I'm subtracting that original 100%. So this is going to be 150, take away 100, which means I have a 50% growth. Okay, we have a 50% growth rate here. And again, you could graph this to just make sure that the pattern is consistent with an exponential. Okay. Next example. Let's say we have the table 0, 100, 190, 281, 372.9. And I have the same question. Is this linear or exponential? And then find all the features. Whatever one you say, you're going to find all of those important features. So I'm going to do a quick linear test first. Definitely changing by ones. I can see just by this decimal that this is not changing by the same number. So linear is out. Let's see if this is exponential. I'm going to divide sequential outputs. So I want to see if 90 divided by 100, what does that give me? That gives me 0.9. Put that directly in your calculator. I want to see if it's the same as 81 divided by 90, because I have to see if this pattern stays true the whole time. That's going to give me 0.9. And I have to see if that's the same as 72.9 out of 81. And I wind up with 0.9. So I have a constant multiplier. So this is exponential. Again, what's the reason? Because it has a constant multiplier in the output for every one change in input. And not only did I figure that out, but that also means that my factor is that multiplier. My factor is that number, it's 0.9. Both this and the pattern that I'm spotting in the table tells me this is decreasing. So this is exponential decay. Remember, all those things have to mesh. If you notice a decreasing pattern, I should have a factor that's between 0 and 1. Do I have a y-intercept here? I do. My y-intercept is 0, 100. Remember, y-intercept always occurs when x equals 0. And now, can I figure out the rate of decay? Well, my factor is 0.9. That tells me I'm keeping 90% if I was to convert this to a percent. I take away the original 100%. And again, I'll write the formula one more time. Factor times 100 minus the original 100. Okay? So this becomes 90%. Take away the original 100%, and I lost 10%. So you can either say that the rate is negative 10%, or you can say that there is a 10% loss, okay, or 10% decay, or however you want to phrase that. That part is up to you. Remember, mathematics is the study of patterns, okay? So if you can spot the qualities of a linear and exponential, that is going to lead you to the rest of these answers, okay? So that's what you want to be asking yourself. You can't just jump into a problem without having some knowledge of what you're looking for. So this is taking us through what are we looking for? What makes those qualities? What qualities am I trying to find? Next example. Let's say I have my input and output, and I have 0, 100,000, not always going to be small numbers, 2, 70,000, 5, 25,000, and then 6.5, 2,500. And I'm being asked linear or exponential. I'm just going to do some shorthand this time, so I don't have to write the same thing all the time. And then find all the features. All right, I'll give you a little hint. It's not going to be exponential because I don't have a change of 1. In our class, okay, at this level, we're not going to see exponential change without x changing only by 1s. That doesn't mean that that's not going to happen in later classes. In later classes, you are going to learn how you can figure out the pattern if it doesn't change by 1. But right now, we're not. So that's a little side hint, okay? So I want to test linears first, all right? Always linears first anyway, because it's an easier test. This is changing by 2. This is changing by 3. And this is changing by 1.5. Okay, I'm just looking at these differences. This is changing by negative 30,000. I'm losing 30,000. This is changing by negative 45,000. I'm losing 45,000. And then this is changing by negative 22,500. Okay, negatives again because I'm dropping, I'm losing. Now, remember what linear means. Linear means I'm looking for a constant pattern. I don't see one explicitly here because all the numbers are different. However, remember that it's rise over run. These guys work together, they're paired together, which is also the change in y over the change in x. I need to see if this relationship stays the same. So I need to see if negative 30,000 over 2 causes the same change as negative 45,000 over 3 and the same change as negative 22,500 over 1.5. I need to see if these changes cause the same pattern. This means I'm really losing 15,000 for every 1 if I simplify this fraction. This means I'm losing 15,000 for every 1. Interesting. It can all boil down to the same fraction. And this, again, directly in your calculator, same thing. I'm losing 15,000 for every 1. That tells me that I could, if I really wanted to, go back in here and fill in the missing values because I don't know what happens when x equals 1. When x is 1, this is supposed to lower by 15,000. So I can fill in the gap, be 85,000. And I can fill in all those other points that are skipped over here because now I can see that it really is the same pattern. So now I can say this is linear and I can describe it for every 1 change in x, the output decreases by 15,000. So I can say that it's linear. I can spot the y-intercept. The y-intercept is 0, 100,000. So I know increasing or decreasing, I know the rate of change, and I know the y-intercept. Okay, the last one we're going to do for this video is this one. We have our input and output, and we have 7, 8, 9, 10, and we have 29, 39, 51, 65. And it's the same question, linear or exponential. Let's do each test. These are all changing by ones. It's a good start. Okay, easier to spot a pattern that way. This changes by 10. I can already see it's not the same change, okay? It changes by 10, and then it changes by 12, okay? I don't even have to go any further. It's not the same change, so it can't be linear. These are changing by ones, 7 to 8, 8 to 9, 9 to 10, difference of ones. So I can also see if I have a multiplier. So I need 39 divided by 29, 51 divided by 39, and let's see if they're the same. Again, directly in your calculator. This is approximately 1.3448, and this is approximately, and notice how I'm using a squiggly equals, because I'm approximating, it's not exact, 1.3077. Are those the same multiplier? They don't look the same to me. They're pretty close. I mean, 1.344, 1.3, but it's not the same, okay? There's a difference here. So if this is not the same multiplier, then it's not exponential either. And all I can say here is that it's none of these. I don't know what kind it is, but it's neither of those, okay? And I can't make any other statement there. So I hope this explained how to do the table, and you also had the previous video of how to do graphs. I want to direct your attention to this sheet that's in your book. It happens a few times actually in your textbook. I love this sheet. I actually have a copy of this directly in Blackboard for you to reference because this is very important. This will be a summary of everything we learn for each type of function that we're going to be exploring. So I would highly recommend that you have this as a reference while you're doing your practice problems, because it will help you to decide what information you have, what information you need, and how you're going to use it. So this happens to be page 73 of your book, but it does occur on other pages as well. So I just want to make sure you have that as a reference. If you have any questions, please ask it when we meet, okay? Or you can contact me via email. I will see you in the next video.